Hi and welcome to Unit 1, Topic 2, Video 7. And in this video we'll be talking about the scalar resolute. Now, just want to point out some language differences here for you. We're talking about the scalar resolute here, whereas we talked about the vector projection in the last video. In some places, and this is typically we use resolute for scalar and projection for vector, but in some places they're kind of interchangeable words. So if you see the word scalar projection, think scalar resolute. If you see the word vector resolute, well, think vector projection, because at this level there's not a lot to discern between those two words. The scalar resolute of A on B is the magnitude of the vector resolute. So I've used that word vector resolute there. So basically we're just saying we want to know what the magnitude of U is, and we discard the direction, which is a bit of a shame because the direction is the easy bit, we already know B. So let's have a quick look at what that means. The scalar resolute is the magnitude of U, which means it's the magnitude of A cos theta, and that is also the same as the magnitude of A times the magnitude of the unit vector B cos theta, because we know the unit vector B here is equal to 1. So again, this is one of those magical steps where you go, well, why would you do that? But we do that because it comes out nicely like this. This is our geometric interpretation of the dot product, where we go A dot B hat. And we could also write that down as A dot B over the magnitude of B. So there's a development of our two main formulas, 1 and 2. They're pretty close, to be honest. I generally just stick with 1 and I can develop B, the unit vector B, if I need to. But it is also a scalar. So we're doing a dot product, we don't then multiply by a vector, so of course this will provide us with a scalar quantity, a single number. Okay, an example. Let's find the vector projection of Q in the direction of S, where Q is 3i plus j and S is 2i plus 3j. So this is an example of a vector projection. So the vector projection formula, you remember, is that U, our vector projection, is equal to, in this case, Q dot S over S dot S. And remember, when we developed this, it was the vector projection of A onto B. In this case, it's Q into S, so our Q is our A and S is our B. And then we multiply this by the S vector. So this is equal to Q dot S. Q dot S is just these coefficients. Remember, this is our 1, 2, and this is our 3, 4. So Q dot S is 3 times 2 and 1 times 3 is 9. Over S dot S is 2 times 2 and 3 times 3 is 13. Times by 2i plus 3j. And I'm going to write this out as 18i, actually no, I'm not. I'm going to write 18 over 13i plus 27 over 13j. It's often a good idea to do our final answer still in component form, completely expanded component form. Example 2, vector A is equal to ki plus 8j, and vector B is equal to 4i plus j. Determine a k such that the scalar resolute of A on B is 10. So we know the scalar resolute in this case, and we want to determine a k to make that happen. So I'm going to recognize here that the scalar resolute, which is the magnitude of U, is going to be equal to A dot B hat. So that's one of our formulas. Now I know A, I just don't know B hat. So the magnitude of B is equal to the square root of 4 squared plus 1 squared, which is equal to the square root of 17. And so I'll be using that square root of 17, and I just do B over the magnitude of B, which is pretty easy. B over the magnitude of B is 4 over root 17 I plus 1 over root 17 j. And so this is going to be ki plus 8j dot 4 over root 17i plus 1 over root 17j. In hindsight, if I'd left that 1 over root 17 out the front, it probably would have made things a bit easier. But here we go. I want this to be equal to 10, 4k over root 17 plus, that's k times 4 over root 17, 8 over root 17, that's the wrong way around, is equal to 10, and now I'm just rearranging to solve. And so this will be 10 minus 8 on root 17 is equal to 4k over root 17, and then I rearrange this. I bring the k over, and I have root 17 over 4 times by 10 minus 8 over root 17, and this will simplify reasonably nicely in that I get 5 root 17 over 2 minus the 8 and the 4 cancel out, the root 17 and the root 17 cancel out, leaving me with 2. So k is equal to 5 over 2 root 17 minus 2. And that is the best we can do. So there we have our scalar resolute and the second part of our vector projections video series. All the best.